Hello and welcome to lesson 42 of my DP chemistry curriculum. Today we're going over structure 2.2.5. We're talking about bond polarity as it results from the difference in electronegativities of bonded atoms. And we will be able to deduce the polar nature of a covalent bond from electronegativity values. Other things to know about this is bond dipoles will be shown with either partial charges or vectors, and we'll talk about that. And all your electronegativity values are in the data booklet, specifically section 9 of the current data booklet. So without further ado, let's go into the lesson. So we have to remind ourselves, well, what's a covalent bond first? Which we've talked about quite a bit in the past few videos, but a covalent bond is an electrostatic attraction. So that's going to be between two oppositely charged things, attraction between two nuclei and shared electrons. So that is the basis of our bond. And the thing is, these electrons can be shared equally or unequally. So we need a way to figure out how they're being shared, because what if one of these nuclei is more positive, or also one of these nuclei is closer to those electrons? They might have a greater pull on those electrons overall. So that's where we bring in electronegativity. Now, with electronegativity, which I will abbreviate to EN from the rest of this, we did discuss this in video lesson 30 of this, where we talked about the trends and what it is. But if you didn't watch that and you just need a reminder, this is a measure of the strength in which a nucleus pulls on shared electrons. So there's a lot of things that we can talk about that affects the strength, but we can just talk about electronegativity as an overall generalization for that strength. Uh, and furthermore, electronegativity, the values are from values range from 0 to 4. This is developed on the Pauling scale, which doesn't actually have units. These are absolute values, but you could also say Pauling units, but nobody really cares. We just put them 0 to 4 as whole or as numbers or decimals. The last thing is that while you do have your data booklet, which holds all the values, if we just look at the periodic table, a good thing to remember is that electronegativity increases as we move towards fluorine, which has the highest. We ignore all the noble gases because they do not have shared electrons because they do not bond. So, with these two ideas in mind, that the covalent bond is that electrostatic attraction between the nuclei and electrons, and electronegativity is the strength of that attraction, we can start looking at bonds. So if we look at a hydrogen bonded to hydrogen in H2, and we look at their electronegativity values, which hydrogen has an electronegativity of 2.2, and therefore it's also 2.2, these are going to be pulled evenly. And if we look at the electrons around hydrogen and we look at this electron density, we're going to get this nice kind of even electron density between the atoms. And this would be an even sharing of electrons or equal sharing. Equal sharing. They're going to pull with the same strength. However, if we look at HCl with hydrogen and chlorine, first off, chlorine is far larger than hydrogen, but chlorine also has an electronegativity value of 3.2. It's a full one value stronger. And so the electrons are going to sit closer to chlorine in this. So when we go ahead and draw these clouds, we notice that it's much more weighted towards the chlorine. The electrons are more likely to be in the chlorine's region. So this is where we start looking at what we call bond polarity, or polar versus nonpolar bonds. So let's start moving into what that means. So what does it mean to be polar? Generally, it's a good idea to know what these words mean in context. You may have heard of the North Pole, the South Pole, or magnets have poles, batteries have poles. Generally, when we refer to polar, what we're talking about in science are oppositely charged ends. Now, in covalent bonds, we don't have charges. This makes sense in maybe NaCl, where Na is positive and Cl is minus. And when we look at these bonded, we can see that this side is negative and this side is positive, and that's a very clear polar bond or polar ionic bond because, well, we have two oppositely charged ends. But when electrons are shared, we generally say that these don't have a charge. So let's rectify that. So when we go through that, what we're actually going to start off is looking at nonpolar bonds first. So when we look at nonpolar bonds, and we go back to our hydrogen example with those evenly shared electrons, we can look at the electronegativity difference, which between 2.2 and 2.2, the difference is 0. If we look at something like maybe oxygen, which bonds in a double bond, and I'm going to use a standard Lewis diagram, oxygen has an electronegativity value of 3.4, much larger, but the difference between them is still 0, meaning that electrons are shared equally. So these are what we call nonpolar bonds. Generally, what we say is that for a nonpolar bond, the electronegativity difference is from 0 to 0.4, somewhere in that range. This would generally say that these are either nonpolar or very weakly polar. When we say weakly polar, while they still do have some polarity, the difference is we kind of almost assume it's near negligible compared to either another molecule, another bond, or another aspect in this molecule that we're looking at. So anywhere from 0 to 0.4, we call these nonpolar or weakly polar bonds. So now let's move over to polar. We need to start getting opposite charge ends for it to rightfully have that name. So let's look at polar bonds. These have an electronegativity difference of somewhere from 0.4, so 0.4 is kind of that weird line, to 1.7 in those values. Now, let's look at an example of a bond that matches that criteria. So let's look at HCl, hydrochloric acid. Hydrogen bonds with chlorine, and we already know from earlier this is 2.2 and this is 3.2. Therefore, our difference is 1.0. That is right in that range. So this would be a polar covalent bond. And what that specifically means is that the bonded electrons are closer to chlorine. Specifically, they're closer to the, oops, that's a horrible M, the more electronegative atom. So let's describe what that means for this bond as a whole. So in this polar bond, a couple things happen. The electrons move closer to more electronegative atom. When that happens, the electron density is higher at more electronegative atom. What we might say is that it's electron rich. Furthermore, the electron density is lower at less electronegative atom. In other words, it's electron poor. This is now the crucial part and where we actually get the name polar from. Because electrons are not fully transferred. So when they're fully transferred, we call this an ionic bond, but they're not fully transferred. The electron rich and poor areas, or instead of areas, atoms, develop partial charges. So they don't become full ions, they become almost kind of like partial ions. And we denote this with this symbol. This is a, whoops, this is a lowercase delta. It looks like an S with a tail. And this means partially positive, and this means partially negative. So we can look at an example where this might happen. And one of the most famous examples is water. When we look at water's diagram, it looks like this, and oxygen has its two non-bonding pairs. We remember that oxygen has a value of 3.4, while hydrogen has a value of 2.2, meaning the electrons move towards oxygen. Therefore, oxygen is going to become electron rich, and it will develop what we call a partial negative charge because it has almost more electrons. Not a full electron more than its protons, but it's sharing a greater portion of those electrons with itself than with hydrogen. Meanwhile, the hydrogen each become partially positive as the electrons are moving away from them. So these hydrogen have one proton still, but they kind of only have like maybe half an electron because their electron is moving closer to oxygen. So in this example, we see that water has two polar bonds. We know it's polar because the difference is 1.2 if we subtract them. And a good rule of thumb, a mantra that you can say to yourself every single day, look in the mirror, say it to yourself as a form of positive self-talk. The more electronegative, the more partially, well, I'm just going to use a symbol, the more partially negative. This is the key to all bond polarity, and turns out it will come up way more than just bond polarity and molecular polarity. This will come up in organic chemistry. It'll come up as we look at reactions. It's going to be so crucially important for you to keep this internalized. So just remember, the more electronegative, the more partially negative. Therefore, the other one's going to be partially positive. All right, so the last aspect of this lesson is what we call dipoles. Dipoles are basically just two separate, oops, separate opposite charges. In a polar bond, you do get two separate opposite charges. They aren't complete charges, but we have two separate ones. Water, we have two sets of dipoles, but we do get these two separate opposite charges. We can show this with what we call a dipole moment. A dipole moment is a vector that shows dipoles. Now, just going into a little more separating and defining words, a vector shows direction and magnitude. If you ever watch Minions, you'll know that because Vector says he has direction and magnitude. So the direction is the direction of the dipole, and the magnitude is the length or the strength of the dipole. A dipole moment is represented with this arrow. This arrow tells us the length is well, not equal to, but proportional to the magnitude. of dipole. And if we highlight certain areas of it, the back looks like a positive and the front looks like a negative. Therefore, our dipole goes specifically from the partially positive to the partially negative. So if we look at HCl and we identify our partial charges here as partially positive to partially negative, we can see that our dipole moment looks like that. Furthermore, if we were to look at something even more electronegative, like maybe HF, where F has a value of 4, while chlorine's was 3.2. So in this case, this is partially I'll keep my colors consistent. This is partially positive, this is partially negative. We would expect our dipole to be larger than in our previous one because there is a greater difference in electronegativity. This has a difference of 1.8, while this has a difference of 1. Therefore, we have a larger dipole moment. So this is what we're going to do to represent dipoles within molecules. And we can do this within not just the bonds, but in a molecule overall, which we will go over in a couple sections. So anyways, I hope this helps and have a great day.